we're going to start by reminding ourselves of some things that we already know. So at the very top there, if we start reading, I've told you that in the later sections of Chapter 6, which I know we don't do chapters, but you can say then in our next unit, we're going to learn some different methods to solving polynomials. Right now we just know how to solve by factoring. And then I'm taking you back to something you should already know. Remember what the solutions of quadratic equations represented. Well, when you solve quadratic equations, your answers always represented the x-intercepts of the graph. Well, that doesn't change when the polynomial is not a quadratic. When you solve polynomials, the answers are still the x-intercepts. There's just more of them, usually. The two most important things to recognize about a polynomial function is its degree, which, remember, the degree is the highest exponent listed, and its leading coefficient. Remember, that's the coefficient's the fancy term for the number in front of the variable. Leading means it's the one very front. When you know those things, you can determine one main thing about the graph, which is a pretty important aspect of the graph. Does the graph eventually rise or fall as you move along the x-axis? We call this end behavior. To determine the end behavior, you're going to apply what we call the leading coefficient test. Now, this test is just a visual test of the actual function. Okay, split it down the middle. I was trying to think how I wanted you to organize this. And draw 4 little graphs here. Okay, this section up here, this is for if your degree is odd, then it would be one of these two scenarios in the top half of the box. In the bottom half of the box, these two scenarios are going to represent if your degree is even. Now, by odd and even, I mean like an odd degree would be 3. So if you have a cubic, or if you have a quintic, or if you have something raised to the 7th, those are odd degrees. Degree that are even would be like a square, or a quartic, or something raised to the 6th. So we're going to start with if your degree is odd. Draw a little representative graph here. So if your degree is odd and your leading coefficient is positive, the end behavior is on the left, it's headed down towards negative values, and on the right, it's headed up towards positive values. So the end behavior would mean it's falling on the left, and then as you move forward left to right on the graph, you're going to end up rising. Okay? So that's if the leading coefficient is positive. And then draw another curve down here, over here. This would be if the leading coefficient is negative. If the leading coefficient is negative, then the end behavior is the opposite. So that as you move left to right, you go from rising to eventually falling. How I keep it, well, how I kind of remember that is when you have a leading coefficient that's negative, so if the first number listed in your polynomial is negative, then you know that eventually the graph has to head towards the negative values. So I always start with this side first, like draw the arrow left or down, and then I just know the other one is opposite of that. So that's if your degree is odd. Your end behavior is going to be opposite of each other. If the degree is even, and you've seen scenarios like this, quadratic, the degree is even for a quadratic. If your leading coefficient is positive, your end behavior is up and up. And we've kind of already done this. This is like if when you're talking about your A value. If your A value is positive, then you know you open up. If your leading coefficient is negative, we're going to draw a little quartic here. then the end behavior is down and down. Now we talk about end behavior because end behavior actually helps us sketch the graphs that we're going to start sketching on the next page. We always start with the end behavior test, and how you show me you've done the end behavior test is really just drawing arrows to show me what the end behavior should be after you're done graphing. Okay, so if you need to pause it to continue writing stuff down, I would do that. And then when you're ready, go ahead and flip the page. Now we have 4 examples that we do together with graphing. We're going to probably do the first one, maybe even the second one together. So before we do that, repeated zeros. Now repeated zeros, very top here. When you have answers that are what we call like double roots, we talked about those when you get an answer twice, that's the same thing. They do mean something special about the graph. With double roots, the graph will touch the x-axis but not go through it. Think of with quadratics, when we were graphing quadratics, if you got one answer, we would say that was a double root, and we'd also say that that one answer represented the vertex touching the x-axis. So this is kind of the same concept. We're just going to be taking it one step further with polynomials. Triple roots, which are much less common, what happens with the graph is that the graph will, let's say this, will flatten out on the x-axis before it goes through it. And we'll do examples of that one, but that one's much less common. So really, the one that you're going to be focused on, and like I probably won't test you over this one. We might look at an example of what it might look like, but the double roots one, you will definitely have a graphing problem like that. Okay, so now we're ready to graph. We've gone through the very basic pieces. The first step we always do is we apply what we call the LCT, the leading coefficient test. Then you find the x-intercepts of the polynomial by factoring, and we're going to set each factor equal to 0 and solve for the zeros, roots, x-intercepts, however you want to think of it. We're going to plot a few additional points, so make a little table of values, and then we're going to draw the graph after that. Keeping in mind that if some of our answers are double roots, that's going to come into play when we graph. Okay, the first one that we look at is going to be function 2x cubed minus 6x squared. Okay, so the first thing that we look at is applying the leading coefficient test. Leading coefficient test is based off 2 things. First, the degree of the function, so my degree is 3, which means it's an odd function, and the leading coefficient. So I have an odd function, or an odd degree. I have a positive leading coefficient. Since it's an odd degree, I know my end behavior is going to be opposite, and because it's a positive leading coefficient, I know eventually, as I move left to right, my graph has to head up towards positive values. So on the left part of my graph, my end behavior is going to be going down. On the right part of my graph, my end behavior is going to be going up. That's the first thing. The second thing would be to find the x-intercept. So we're going to find the x-intercepts by setting my function equal to 0, because that's really what I'm trying to find when you find the x-intercepts. You're trying to see where your function is going to give you a value of 0, and that's the x-axis is where all the y's are 0. Now, just looking at this, you might not look at it and say, oh, I can factor that because it's not really a difference of squares. You can't take the square root of 2 or 6. Excuse me. But the first step to factoring is always to try to pull out the greatest common factor. So I'm going to pull out a greatest common factor here. And we're going to set both those equal to 0. So 2x squared equal to 0. X minus 3 equal to 0. So I get 3. In this case, I'm going to get 0 as an answer, because if you divide by 2, 0 divided by 2 is 0. Then you take the square root of both sides. Well, because I have to take the square root of both sides, whenever you do that, you get a plus or minus. You can essentially say you have plus or minus 0, but that doesn't really make sense. So I'm going to put 0 double root. This means the graph will only touch here. Now, to get a good baseline for my small table of values that I have to make. Hi.
Do you have a second to just meet a new student?
Yeah. Sorry. Give me like 5 more minutes.
No problem.
Thanks. You're going to mark 0 and mark 3. And we're going to kind of talk through what this graph is going to look like. You know the end behavior is going down. I know at 0, my graph will only touch here, so I'm not going to go through the graph there. I'm only going to touch. But I do have to go through the graph here. So if I come up like this, because my end behavior has to be going down on the left. So if I'm following my curve, it should come up here. Touch has to bounce back down, but it does have to go through this spot here. So somewhere between 0 and 3, I have to make a loop back up so I can head up towards positive values. That value between 0 and 3, like I need to know how short that loop is or maybe how long that loop is. So to figure that out, I'm going to pick the in-between value between 0 and 3, which is 1.5. And we're going to plug that in. Now to plug it in, I'm just going to use the store feature here because it's probably going to be the quickest. So I'm going to store the store button, that one there. I'm going to store 1.5 as my x, since I only have to put in one number there. And then I'm going to put in the equation, how it's written. And then the calculator reads my x as the value 1.5, and I get the y value of negative 6.75. Okay, if you're wondering where I got that 1.5 from, the 1.5, well, let me back up. Polynomials are always very symmetrical. So with a symmetrical polynomial, I know that it can't be like some weird value between 0 and 3 where that loop is going to occur. It's going to be symmetrical. It's going to be right in between them. So 1.5 is the in-between value between my two x-intercepts. Plug that in to get my y value. I'm going to mark that 1, 2, 3, 4, 5, 6. So right here. And then you're drawing your curve. Comes up, just touches, loops back down, loops back up. And so to check your end behavior, this arrow should match this arrow should match this arrow. And they do, so you know that you've graphed, at least by end behavior, you've graphed it correctly. And we always talk about domain and range. Now, the nice thing about polynomials, especially with cubics, your domain here is going to be all reals. Range is going to be all reals. You can plug in any x you want, and you can get out any x you want, because both these sides are going to go forever and ever in both directions. Let me just take a look at the time here. Okay, well maybe just a minute of review, and then I'll cut it short because it's almost 15 minutes. So, as a reminder, when we solve polynomials, the answers give me my x-intercepts, and behavior is the first place we always start, and it's based off the leading coefficient and whether your degree is odd or even. Now we've only done odd degree type functions, so obviously we'll be practicing more of those. Double roots is really the one that you need to make sure that you remember. That just means if you get an answer twice, the graph will just touch the x-axis at that point, but won't go through it. These are the steps written out on how to graph, and then that is the one equation. Now in the last minute here, let's just say you had to graph a function that was not factorable. If that happens, you can always graph anything by using a table of values. So, you know, if I wasn't able to factor this and I still expected myself to be able to graph it by hand, or at least sketch it a little bit by hand, I might just come up with a table of values and go maybe from -10 to 10 and just graph a bunch of points in order to get a nice shaped curve, just so I kind of had a clue on what it looked like. Plus, even if this wasn't factorable, I would still be able to determine the end behavior to give me kind of an idea of where to go with it. So the homework video for Friday will be basically finishing up this note packet with these 3 examples, and we're going to be working on graphing, so this might just be a review on Friday, but we will see. And actually, you know what? Now that I think about it, you might get to do that in class on Friday. We'll see. Anyway, so we're done. I'm ready to work tomorrow.